Okay, what we did last time was we started doing the standard functions and their graphs. We did domains and graphs. This time what we're going to do is I'll relist the standard functions and their graphs, a basic list of the ones that they expect you should know. I won't barrage you with all the different kinds, but we'll do most of the standard ones that they talk about. And then we'll do transformations. There's 5 categories of transformations, and then there's 2 in each sort of. So there's about 10 transformations, but then we'll organize them and we'll see how to do this after I drink coffee. All right. So for first of all, the standard functions. Demographic is going to be, the first one was constants, and that's going to be f of x is just some b, a real number, and that's just going to look like a constant function, b. The next category that we had was affine functions, I called it, or straight lines. That's just mx plus b. And we're going to have 2 cases in this category too. One case if the slope is positive. If the slope is 0, we have this case. If the slope is positive, we go like this. And if the slope is negative, we are decreasing, increasing, decreasing, whether your slope is positive or negative. The next category we have, which are the building blocks, are going to be, I can't switch the pens colors and drink my coffee at the same time. Power functions, which are the main building blocks. The other 2 reference it. So power functions where f of x is x to the n, where n is greater than equal to 2 is a positive integer. And there's going to be 2 cases now for these next 3 categories based on whether n is even or odd. If n is even, what do we get? We get roughly the u x squared. If it's odd, we get this guy, and they'll all roughly look like that if they're odd, and they'll all roughly look like this if they're even. They get more square and sharper a little bit here. The next category is the inverses, what we would call them inverse functions of this, in case you want to know. We may discuss this later, I'm not sure. I'll sneak it in somewhere. But in composition is the etc. I'll do the addition and compositions, try to squeeze that into this video also, or lecture. And so what we're going to do with that is when we compose a function and its inverse, you get the point back, x. What is this going to be? This will be nth root. Nth root functions are going to look like f of x is the nth root of n, which is x to the 1 over n. So nth roots are the denominator of a fraction. 1 over. What do they look like? Again, there will be 2 cases based on n even and odd. If n is even, this one fails the horizontal line test for being invertible, so we ignore this. And the inverse will be the graph obtained by reflecting across the line y equals x. So we will get that guy, the square root of x, which is x to the 1/2. If we don't have a restriction, then the inverse is going to be the infinite s, like this. This will be the third root of x. If you compose x cubed and the third root, you just get x back. That's what I mean by inverses of each other. They cancel each other off. The last 2 categories we did last time were, now that we have all those, were 1 over these power functions, so that we can start getting essentially a rough idea of what these rational functions, etc., are going to behave like. So we had 5 reciprocals of power functions. So that's going to be f of x is 1 over x to the n, where n is greater than or equal to 1, is a positive integer. And again, we're going to have 2 cases. And we have to restrict the domain. Also notice we restricted the domain of the square root. But the mantra was you can't have negatives under there. So it is from 0 to infinity. Here we have our other mantra, you can't divide by 0. So if you're doing that, we would have the Atari function. You can only see part of it, but the Atari function is going to be this one, and then if it's even, it will look like this. So 1 over x squared. This is also equal to x to the negative n. So then you can view them all as exponent rules. And here we're going to get 1 over x, the hyperbolas. So this is the rough shape of what they're going to look like. The last one I did was 6. I did the absolute value. Function. What does the absolute value function do? Basically, it's our first piecewise defined function, which is the absolute value of x, which is x or negative x greater than or equal to 0, x less than 0. And this looks like a v. It's telling me when x is greater than or equal to 0, it's just a straight line, y equals x, and we know what that looks like. It should be positive, increasing from 0 to infinity. From case 3, the affine functions, this one's actually linear. And then if you're less than 0 on this part of the domain, you are the line negative x. So this is negative x equals y, and this is y equals x. So this is absolute value function. The other category we have in there is the trigonometric functions, the 6 trigonometric functions. So 7. They'll also do this with the 6 trigonometric. Quickly, the two main ones are sine and cosine from the unit circle. I'll do a whole other section or video just on the trigonometric functions when we do their derivatives, etc. But for now, cos of 0 is 1. Then at pi over 2 we get 0, then negative 1, then 0, then 1. So cos will look like this in its period of 2 pi. So this is going from 0, pi over 2, pi, 3 pi over 2, and then 2 pi is where it hits 1 again. This is cos x. Sine x will have the same main points. Pi over 2, pi, 3 pi over 2, and 2 pi. We're going to use unit circle values to calculate these things. Sine of 0 is 0. At pi over 2 it's 1, 0, negative 1, 0. So then we get sine. And then we can copy it back and forth. This is when we do the curve sketching stuff. This is why we want periodic functions, so we can find what they look like in their period and then just copy it indefinitely. This is called symmetry. The even and oddness of functions will be the other type of symmetry. All right, I'm stepping on magnets. I knocked some off. When we now take these functions, what we're going to do is I'll list all the standard transformations, and I'll sort of give you a pictorial representation of what's going to happen with all these lists of transformations, which there will be a barrage of. You can go back and pause and look at them again, and then I'll list them all, and then I'll do a couple examples at the end of this to move them around. And then if we have time, etc., I'll jam in the addition, subtraction, multiplication, division, and composition of functions, which aren't too bad, and how to find their domains. So this is basically the main functions. There's a whole bunch in here. I didn't draw tan or the other ones, but there's a whole bunch of standard functions where you should know. If I say sine or cos, it's a wave. If I say absolute value, it's a v. If I say 1 over x squared, it's the Atari functions, etc. This is the category that I'm building for myself, and call it a clever, funny name. This microphone, my cameraman, etc. is not here, so I have to do it all myself, and none of the technology works. I don't know why it couldn't be me. But we want to have clever names for, or a way of memorizing all of these different types of standard functions and their graphs, and then we're going to move them around with these transformations. That's the idea. Let's do that. The first category and the most dangerous, technically, because I don't want to get into it, you can do reflections after, but you're no longer reflecting about the coordinate axes. You're reflecting about the lines where you've shifted to. So long story short, just do the reflections first, and then you can do the other categories in any order you want. But category 1 is always going to be reflections about coordinate axes. the x-axis and y-axis. First of all, what's confusing is the x-axis is actually the straight line y equals 0, and the y-axis is the vertical line x equals 0 all the way. When we do this, we can draw pictures for ourselves, and what's happening is we can draw these two things, and then we want to be able to, the idea for this is we want to be able to, from the picture, we're going to give you the picture and we're going to say this is what the algebra is that's representing that, and then when we give you the algebra you have to do it in reverse and say, oh, that means that they're reflecting. So let's draw the picture first. Reflecting about, oh, I didn't finish, it doesn't really matter, but when we're reflecting about, let's do the x-axis first. This is the x-axis. And so when I'm reflecting about there, if I have a functions like that, oh, can we reflect like that? No. That meant that all the points were going across here. That's perfectly symmetric. Move it down a little bit. He's not there. Can we try one more time? Close enough. So what that gives us is the reflection. If this was f of x, we now want to say, or the graph, but I'll cheat algebraically. What do we want to say? We want to say that there's a negative somewhere. And so what gave us the x-axis? This was y, technically, in all the pairs, x, y. And so where did the points go? The x values have stayed the same, if you look, when we reflect, but the y value changes to its negative y. So if you have the function g of x, which is negative f of x, this is reflection about the x-axis. If I do that with a different function, let's make it easier for me to reflect, and then I reflect about the y-axis, you'll notice that now the y value, the height hasn't changed. My x value went from x to negative x. So if it's on the inside, the function g of x, which is f of negative x, if this was f originally, f on the inside of the argument or the brackets tells me if there's a negative, it's a reflection about the y-axis. This is what's going on with reflections. We deal with the negatives first. Sine and cosine, and a lot of functions eat them, whether they're even or odd. Cos just eats a negative. Sine will spit it out, which means it has some kind of symmetry when we do these reflections. But we always do the reflections first, then we can deal with all the other ones. Trigonometric functions even have fancy names, like amplitude is vertical stretch and shrink, and period is horizontal stretch and shrink, etc. Let's look at the next categories. The next categories, what we can do is we'll do the weird ones. It seems like it's backwards for two of the categories, and I'll tell you, and hopefully this is my job description, explain to you why it seems a little bit backwards, and the trigonometric functions are the easiest ones to explain this for. So let's do vertical stretch and shrink and horizontal stretch and shrink of functions. What does that look like algebraically is what we're looking for. Category 2, vertical stretch and shrink. What this is going to look like, again, we're going to have two cases. So in this case, now we have to say we have f of, in the vertical, it's going to be a number on the outside that will stretch and shrink it. Let's call it a times f of x, which is our new function g. And then in this case, we'll have our new function g is going to be a f of x. So what's the different cases? In this case now, when we do in green, this will say if a is between 0 and 1, we'll keep a positive. And remember, we're dealing with the negative with reflections. So if a is positive between 0 and 1, and then if a is larger than 1. If a is 1, you just get the function back. Now what would the graph look like? If we have that, and the best way is trigonometric functions. If we have our original function is like this, if we multiply by a, or I should draw that one in a different color. If our original function is orange, then multiplying on the outside by a small number between 0 and 1, half or something like this, will give you a shrink vertical. And if I have my original function is like this function, and at a, and I multiply by a on the outside, and it's larger than 1, then what's going to do is it will stretch it vertically. That one's the easy one. The next one's backwards. The next one, it seems like in your mind you want it to intuitively, or whatever this means, do it backwards. Big number on the inside means shrink horizontally. Small number means stretch. Let's see why. Category 3 is going to be horizontal stretch and shrink. Again, there will be two cases based on the A being, I'll use A just for simplicity, but I might change them to A, B, C, D or something like this in the final form. And then I'll label what they do. But if we're going to do, so A should be on the outside. Let's do, is B, yeah, okay, let's use B. So if I have on the inside, my new function is f of, say, bx, where now 0b is less than 1. This will actually, what this is actually going to effectively do is stretch us horizontally. And if I have b is larger than 1 in this case, where I have f of bx on the inside of the argument is my new function g, then this will shrink horizontally. Again, trigonometric functions are good to see with this because sine is 2 pi periodic, and if you have a b in there, the period p becomes 2 pi over b. Therefore, if you have a small number in there, let's say b is 1/2, then you're going to get 2 pi over 1/2, which is 4 pi. Do the calculation. You should be able to do this by now. So what is going to happen is, instead of sine being like this, it will stretch from, if this is 2 pi, then I need 3 pi, 4 pi. It's going to stretch. Oh, sorry. I almost copied it out completely. What's going to happen is it's going to stretch, so it'll be 0, 1, 0, -1, 0. It's stretched it horizontally. So this was with the 1/2 on the inside, stretches me horizontally. If I do this with sine, say, of 2x, what the new period will be is 2 pi over 2, which is just pi, so it will shrink it. So now, if I started with 1, 2, 3, 4 as 2 pi, then sine originally would do this. But now I'm going to shrink it horizontally because I use the big number 2. We're going to go from 0 to pi only, so we need tick, tick, and then we would be 0, 1, 0, -1, 0. And we've horizontally compressed or shrink it when we use a big number. So it seems backwards, but we'll practice this a little bit. The last two categories are the easiest ones, which is vertical stretching, or vertical shifting, and horizontal shifting. So 4, let's do, 4 has one that's actually backwards. Let's drink some coffee. And so again, this one will have backwards because x minus c is equal to x plus c. And then if we're on 0, negative c is over here. So when we do shifting, when we say x minus c, when c is positive, that means you go toward, you ignore the negative, you go towards where c would be, which is to the right. When we do x plus c, that's x minus minus c, and minus c is on the left of 0. So when we shift, if there's a plus, you're actually shifting left, and you want the plus to say you want to go right, but it's because you're doing minus minus c, and minus c is to the left of 0, and plus c is to the right, and this is why we get the terminology about what I'm about to do to you. I also have to check. I have another meeting. I got 5 minutes. Good. So we're just doing this, and then we'll do an example. So 4 is horizontal shift, and 5 is vertical. What are we going to do? So I need, so here if D is positive always and C is always positive, or K they might use, then what's going to happen, if I have horizontal shift, if this is f of x, then shifting left does f of x plus c by c units. And if I have, this is f of x, and I have c is positive, then I will be shifting right if I do x minus c inside the argument. For vertical shifting, if d is always positive, then if I have f of x like this, or let's do f of x like this, then adding the number will make it shift up. So this is plus d is up. This one is left. This one is right. And the last one, if I have my function is this guy, f of x, then subtracting d will shift me down. Therefore, we have 5 categories. There's 2 cases in each one. Reflections, vertical stretch and shrink, horizontal stretch and shrink, vertical shifting, and horizontal shifting. Let's do an example. I have a meeting to get to. All right, example. Sketch y equals, or g of x, g equals x minus 1 squared plus 2. I'll do more examples in the next video. I just have to end this video because I have a meeting that I realize I have to get to also. Busy schedule. What we want to do first of all is recognize the standard function. The standard function is going to be x squared, the power function, and then therefore I know that it looks like this. That's the idea. I take the lexicon, I see the squared, it hits a nerve. I didn't even have to do any clever tricks. We'll do a few of the clever dirty tricks next time, but just to show you the basic idea of how I use the standard transformations. And then, so I guess we're not going to do the etc. either. Ignore that part. And so what I want to do is I take the standard function in my lexicon, and then I use the standard transformations, and I try to see it like that. And we try to identify that this is going to be my D and this is going to be my C in the general form. That means I'm going to do what? 1, I can list them. I'm going to shift right 1. And 2, I'm going to shift up 2. And if you know where the vertex is, in this case, the vertex is 0, 0. That's what I focus on moving. So I start from 0, 0. We're going to go right 1 and up 2, and my vertex will move there. And the parabola will do that. This is the graph of this new function. This is the idea of how quick it is and easy it is. What I'll do is I'll cook up a whole bunch of examples of more complicated ones and all the dirty algebra tricks you have to do to get in these forms. And then we'll do a bunch of examples, and then we'll do composition, addition, etc. in the next video. See you soon.